Okay. So good evening. Today's talk is an introductory talk on spectra and stable homotopy category. So this will be, okay, we will elaborate most of the terms that we have seen in earlier talks. So let's start with the outline of the talk. So we will start with the few stable phenomena and come to the notion of stable homotopy groups. Then we will state the Brown representability theorem, which will be the motivation to the definition of spectrum. And then we'll see some properties of stable homotopy category. This actually studies the homotopy category of spectrum. And then we will see some capable candidates for this category, which includes the Spanier-Whitehead category of sequential spectra, category of orthogonal spectra. And we'll see few the advantages and disadvantages of those categories. And we'll conclude the talk with the Spanier-Whitehead duality, a brief discussion on it. Okay, so let me begin with the Freudenthal suspension theorem. So unlike homology and cohomologic groups, we don't have suspension isomorphism for homotopy groups. And this theorem states the conditions under which we will get the isomorphism for homotopy groups. So the statement says that for n-connected space X, the map X2 loop of suspension of X, this induces a map from kth homotopy group of X to k plus 1th homotopy group of suspension of X. And this map is an isomorphism for k strictly less than 2n plus 1. And at k is equal to 2n plus 1, this is epimorphism. So to remember these bounds is one easy example where eta is the Hopf map, which is actually the generator of pi3 of S2. So for the first map, X is S2, which is 1 connected, and k is equal to 3, which is equal to 2n plus 1. So this map is onto. If you take one more suspension, then we have the second map where X is S2, and if you check, then we land inside this condition that k is strictly less than 2n plus 1. So we get this isomorphism. If you keep suspending these maps, we always stay in this condition. Once we have this condition, then we will stay in this condition. So this onwards, we will get isomorphism. So this is not just for a sphere, this is in general true for any topological space X, that if we consider this sequence induced by the suspension morphism, then this sequence stabilizes. So it means after large suspensions, we'll get all the homotopy groups will be isomorphic under the suspension. So we'll define that co-limit of the sequence to be the nth stable homotopy group of a space X, which will be denoted by pi n s of X. Okay. From the definition, it is evident that these stable homotopy groups are stable under suspension. So this is the first property. Then second says that for a relative pair, the n stable homotopy groups are isomorphic to the quotient, n stable homotopy group of quotient space. And the third one, if you have wedge of spaces, then the n stable homotopy group of wedge of spaces will be isomorphic to the direct sum of wedge of individual stable homotopy groups. So we are getting this nice property which are not true for homotopy groups. This is because stable homotopy groups form a reduced homology theory. So let's recall quickly what is reduced homology theory. So it is a covariant functor E star tilde from category of pointed CW complexes to the category of graded abelian groups, which satisfies following 4 properties. The first one says if 2 maps are homotopy, then the induced maps will be equal. Second, for a relative pair, we will get this boundary map, which is from E star tilde of relative pair to the E star minus 1 of A. Third says, given a relative pair, we correspondingly we have the inclusion map and the quotient map. Together with this boundary map, we'll get this long exact sequence. And the fourth one, if you have a set of spaces, then the inclusion maps will induce the isomorphism, this isomorphism. So a functor which satisfies these 4 properties are known as the reduced homology theory. So we already know the singular homology or the cellular homology, the Ram homology, all these are examples. You must have observed that these are the common observations among those properties. Okay. So a simple consequence of these actions is the next lemma, which says the reduced homology theory is stable under suspension. It means E star tilde of X is isomorphic to E star plus 1 of suspension of X. Analogously, we have the notion of reduced cohomology theory. It is a contravariant functor which satisfies the 4 properties which are kind of dual to the previous 4 properties. And here also we have suspension isomorphism. Okay, the next is the important result about the reduced cohomology theory, the Brown representability theorem, which we can also think of as a motivation to the definition of spectrum. So let's see the statement. If you have reduced cohomology theory, then for each n, there is a connected pointed CW complex Kn such that for any CW complex X, we have this isomorphism. So this side is a nth cohomology of X, and this side we have homotopy classes of maps from X to Kn. And these Kns are unique up to homotopy equivalence. So it means given a reduced cohomology theory, we'll get a sequence of CW complexes, Kn. But so now question, is it enough to recover the cohomology theory? But of course not, because we can't talk about the co-boundary maps just using the sequence of spaces. So we need to add more structure to this. So for that, let's observe these following isomorphisms. The first isomorphism is coming from the Brown representability theorem, just we stated. The second is due to the suspension isomorphism. The third one is again using Brown representability theorem. And fourth one is using the adjunction of loop and suspension. So instead of A, if we consider Kn here, then here is this group, Kn, homotopy classes of maps from Kn to Kn. And this isomorphism is written here and this is here. So map the class of identity, consider the image of identity under this isomorphism. Suppose it is mapping here to sigma n and here to sigma n tilde. We'll call these structure maps. So these are going to play a crucial role in the definition of spectrum. And in general, also we can see that these maps are important because this isomorphism is under this composition of sigma n and sigma n tilde. Okay. So now we have sufficient information in our hand that we have sequence of spaces together with the structure maps. And here's the proposition, which talks about how we recover the cohomology theory. So if you have a sequence of CW complexes Kn together with the weak homotopy equivalences sigma n tilde from Kn to loop of Kn plus 1, then we can determine the reduced cohomology theory with this. If we can compute this homotopy classes of maps from X to Kn, we will define this to be the nth cohomology group of X. And the co-boundary maps will be induced by this sigma n tilde. So it means if we have a reduced cohomology theory, we will get a sequence of spaces and structure maps, and other way also true. So that's why the study, we are interested in the study of this spectrum. This is one of the motivations. So here's the definition of spectrum. It is a sequence of topological spaces together with the structure maps. Okay, here, just 1 minute. Here, weak homotopy equivalences are coming. It can be checked from this here also. If you consider if you consider instead of Kn Sn, then you can check these sigma n tildes or weak homotopy equivalences. Okay, and here we haven't added that condition, but when we add that condition, then we will say that spectrum to be the omega spectrum. Now to form a category, it's in obvious way. Morphism of spectra is again a collection of continuous maps Fn from Xn to Yn, and that should respect the structure maps. That means this diagram should commute. Okay, so we are saying this diagram should commute up to homotopy here. And just keep in mind that we are going to use these definitions ahead, but with some extra structure which gives different spectrum. So this is because you may come across with different terms of spectrum. Like we just stated is the spectrum, which is some author also refer that as a pre-spectrum. We have seen this omega spectrum where sigma and tildes are weak homotopy equivalences. If you change that condition into homeomorphism, we will get the strong spectrum. There is a notion of sequential spectrum, simplicial CW, finite CW, orthogonal or symmetric. We'll come across some of, I think, some of these in further talk, but there are also different notions like ring spectrum, commutative ring spectrum, motivic spectrum, then equivalent spectrum, which studies different homotopy theory. Okay. So let's see a few examples. These examples we have already seen in the lectures. So the sphere spectrum, we will fix the notation bold S, whose nth term is the nth sphere, which can be also thought of as the nth suspension of zero sphere. And the suspension, the structure maps are the homeomorphism. So this is an example of strong spectrum. Then similarly, we can talk about the suspension spectrum, denoted by infinite suspension of X with n term as n suspension of X. And again, the structure maps are canonical maps. Now, once we have suspension spectrum, we can shift that and we will obtain the D-suspension spectrum. So just define the first few terms to be the points. And so this is this shift spectrum. The next we have seen the Eilenberg-Maclaurin spectrum. Yeah, and the fourth one is represents the complex topological K theory. So we start with a unitary group UN, like the union over N, we will denote it by U. And now using the Bott periodicity, we have double loop space of U is again homotopy equivalent to U. So we'll use these to define the structure maps such that for this K, the Kn is will define alternating U and loop of U. So this will represent the topological K theory, complex topological K theory. Analogously, we also can define Ko, which represents the real topological K theory. The next example is about forming a spectrum with having 1. So if we have a spectrum X and a topological space X, A, then we can form a new spectrum X smash A. So, okay, this smash is just a formal notation here. We are defining nth term of this spectrum to be Xn smash A. And this is smash of topological spaces. And the structure maps are sigma n smash identity. Okay. So now, analogous to topological spaces, here also we can talk about the homotopy groups of spectra, where we will be using the suspension map and the structure maps consecutively, which will give this sequence. And the co-limit of this sequence we will define to be the nth homotopy group of a spectrum. Okay, so the one property here that this wedge product behaves well with homotopy groups of spectrum. Yeah, so here are some computations of homotopy groups that the examples we already have seen. Sphere spectrum. So this is by definition, but if you observe, then this is the same definition that we have given for the stable homotopy groups of spaces. So here the space is 0 sphere. Here it will be the X. So they coincide, and here it is just D shift. So we'll get the stable homotopy groups N plus D stable homotopy group of X. This we saw yesterday that the homotopy groups of Eilenberg-Maclaurin spaces are concentrated. Only one group is non-zero, others are 0. And about the K spectrum, we know the homotopy groups of U and loop of U. That's why we are getting this alternating terms Z and 0. So this is the example where we have negative homotopy groups of a spectrum. So if you observe this definition, then we are saying that this n is in Z and k is in n, and we can choose a large n such that n plus k is greater than 1. So we can define the homotopy group of spectrum for any n in Z. Obviously, for topological spaces, those will be 0 for the suspension spectrum, but there are examples where we are getting this non-zero. Okay, till now, any doubts? This is about the spectrum. Now we will start about the stable homotopy category. Okay. So about the stable homotopy category, we will see the properties that this category should satisfy. We are not going to prove these properties, or we are not in detail. There are 12 properties, and we actually say that if a category satisfies these 12 properties, then that is a stable homotopy category. So I will focus on those properties that we will need in further talk. So the first one is the infinite suspension and infinite loop are the adjunction functor from, so here from homotopy category of topological spaces to the stable homotopy category. Then, okay, here we'll see this, what is this notation ahead. So this is called the stable homotopy classes of maps of spaces. The condition 3 and 4 together says that this category is additive, and 3, 4 plus 5 says that this category is triangulated. About the sixth one, we must have seen this for topological spaces. If you're okay, then you can take the smash with S1. This will be just give the suspension of x2y is isomorphic to the x2 loop of y. So analogously here, we are talking about x and y are spectrum. Similarly, f of ay is a spectrum, and A is a topological space or a CW complex, this identity. And we can talk this same identity here, where all x, y, z and f of y, z are spectra. But for that, we need to mention what is this smash of spectra. And for that, we need this monadal product on this category. So, okay. But we'll assume that these properties hold for the stable homotopy category. Next, given a spectrum, we can define a reduced cohomology theory such that for given x, the nth homology group of x is given by nth homotopy group of E smash x. Similarly, given a spectrum, we can define the reduced cohomology theory so that A will map to homotopy classes of maps from infinite suspension of A. So this is suspension spectrum to E. So this will be the nth class. Okay. And similarly, other way is true for the cohomology theory. If you have a cohomology theory, then we'll get an object E such that nth cohomology group of A will be given by this. So maybe I'll just mention what this negative means here. For a while, you can say that we have some negative suspensions, and this is not just this term, this negative A means. And last is, if you have a map, then it will induce a map on cohomology theory. So a category that satisfies these 12 properties will be a stable homotopy category. Okay. So now let's see some candidates for this category. We'll start with the Spanier-Whitehead category, which was actually the first attempt to form a stable homotopy category. So this statement is the generalized statement of Freudenthal suspension theorem. If you consider this, if x and y are CW complexes, and if you consider this sequence induced by the suspension maps, then this sequence stabilizes. Sorry. So here observe that, just note that the homotopy classes of maps from K suspension of A to B, this is a group if we are taking at least one suspension, and if you are taking more than one suspension, then this is abelian group. This admits a abelian group structure on it. So if we just forget first two, then the sequence is actually the sequence of abelian groups, and its limit will, the co-limit of this will be admit a abelian group structure on it. We will define that to be the stable homotopy classes of maps from X to Y. So it is denoted by this notation or S. These are the stable homotopy classes of maps from X to Y. Okay, simple observation that it is preserved under suspension. We are going to use this. So now let's talk about the category. So the object of this category are the suspension spectrum, where A is finite CW complex. And object of this category are the stable homotopy classes of maps from A to B, which can be also denoted by this. Okay, before talking about whether this is a stable homotopy category or not, let's see a few nice properties of this category. So, okay, 1 minute. Okay, consider a relative pair A inside B, then consider the co-fiber sequence induced by this map and apply the contravariant functor to, we'll get this long exact sequence. So this will end here. We cannot extend in topological category, homotopy category of topological spaces. But if you consider the sequence in this, this category, we'll get this sequence and use this property that these are suspensions. Here is suspension. It is preserved under suspension. So this sequence, nothing but we are talking about this sequence. So we have suspension. We cannot extend it. We say that, I mean, in topological category, we cannot extend it from this onwards. But since we have suspension here, then we can again extend this sequence and keep replacing. We can extend this ahead all the way. So we'll get actually this sequence, extended sequence. So now here, coming from left side, we are taking suspension on the domain, and after some time we are taking suspension on codomain. Just to avoid this, we'll add formal desuspension of these objects. So for any X in this category, we'll add negative suspension of X. Now, once we have added some objects to the category, we should tell what are the morphisms coming out and from that object. So we'll define the the stable homotopy classes of maps from negative suspension of A to Y is just homotopy classes of stable homotopy classes of maps from X to N suspension of Y. And similarly in this case, so we are just shifting these suspensions. Okay. Yeah, so just this modification will give us this long exact sequence, and so where the suspensions are in Z. Similarly, if you consider the same co-fiber sequence and apply the covariant functor on it, then we'll get this sequence, but this is not always an exact sequence if you apply the covariant functor on the co-fiber sequence. But if we consider this sequence in this Spanier-Whitehead category, because of this fact that after large suspensions, the suspension of A will be homotopy equivalent to the fiber of next map. So that sequence actually behaves like a co-fiber sequence, and and again using the last logic technique, we can extend that sequence on the left-hand side. So we'll get this sequence obtained from the co-fiber sequence. So in this category, the co-fiber sequence and fiber sequence behaves equally. This is because this category is a triangulated category. So here are these two first 2 points will say that this category is triangulated category. And further, this category is also the full subcategory of stable homotopy category, but not the stable homotopy category. And this is because the major drawback of this category is it cannot represent all reduced cohomology theories. That was one of the important conditions from the stable homotopy category. So the For example, the K theory, we cannot represent K theory in this category since we have the objects are suspension spectrum obtained from the finite CW complexes. Okay, so next candidate is the sequential spectrum. These two definitions are same that we have started with. The definition of spectrum coincide with this sequential spectrum and omega spectrum. But the change is in the morphisms that this diagram should commute strictly, not up to homotopy. So this will form the category of sequential spectra. We will denote it by SN. Here is next definition is about the homotopy between two maps of spectra. So if we have F and G, the maps of spectra, then we should get this H. So this definition just says that this H is again a sequence of spaces, sequence of maps Hn from Xn smash I plus to Yn, which will give the homotopy between Fn and Gn. So it is level-wise homotopy. Yeah, the next definition is about the pi star isomorphism. Analogous to topological spaces, here also we can define the pi star isomorphism. So a map of spectra is said to be pi star isomorphism if the induced map on the nth homotopy level is isomorphism for all n. This is some equivalent criteria of a map being pi star isomorphism. And this category has all small limits and co-limits, which are defined level-wise again. So now we want to talk about the homotopy category. So we must know what is the model category on it. Here, the model category is the stable model category. For that, we need the 3 morphism classes. So the weak equivalences will define with the pi star isomorphisms. The fibrations are stable fibrations. So it is a little constructive term which is defined on this page number 62 from the first reference. And the cofibrations are Q cofibrations. So with this stable model structure, on the category of sequential spectra, we'll say this is the stable homotopy category. So we define the stable homotopy category as the homotopy category of sequential spectra with this stable model structure on it. So yeah, to say this is stable homotopy category, we need to check all those 12 properties and that are checked here. Yeah, so even if we obtain the stable homotopy category, still we are talking about the further candidates. This is because this category don't have the commutative smash product on it. To do some good operations on this category, we need the cup product, cap product, and for that we need the commutative smash product. So that's why here comes the next category, the category of orthogonal spectra. So for that, let's recall few definitions. So a group G, so let G be a group, and a pointed topological space X is said to be a G space if it has a continuous group action on it. And a map F between the topological G spaces is said to be a G equivalent map if f of G of X is equal to G times f of X. Yeah, so this should satisfy for all X and G. So here's the definition of orthogonal spectrum. So it is a sequence of pointed topological spaces Xn with this following data. The Xn should have a continuous action of, here the group is unitary group, and there should be maps sigma n from suspension of Xn to Xn plus 1. And the composition map sigma nk, which is from k sphere smash Xn to this Xn plus k, should be OK cross On equivalent. So this is just a sequential spectra with the group action on the spaces, and the maps are unitary group equivalent. again, the morphisms will be the unitary group equivalent maps, and they should they should respect the structure maps. Yeah, so with this, it will be a category. We will denote it by okay, sorry, OSO. This category also has limits and co-limit, and these are defined level wise. Now, as we stated that this definition we are obtained from the adding some structure on sequential spectra, we have the forgetful functor from the category of orthogonal spectra to the category of sequential spectra. And this functor preserves all the limits and co-limits. So, okay, for next term, we are going to use this forgetful functor, give the model structure, stable model structure on this category. So the weak equivalences in the category of orthogonal spectra are the map is weak equivalence if the image of this map under this forgetful functor is pi star isomorphism in sequential spectra, category of sequential spectra. And similarly, the map is a stable fibration if its image under this forgetful functor is a stable fibration in sequential spectra. So with this, we have the stable model structure on the orthogonal spectra, where the co-fibrations are Q co-fibrations. And here's the theorem which says that the category of orthogonal spectra equipped with this stable model structure is Quillen equivalent to the stable model structure on the sequential spectra. So these categories are Quillen equivalent. Next comes the symmetric spectra. The definition is analogous to the definition of orthogonal spectra. Just change the group from unitary group to the symmetric group, sigma n. And similar about the morphism set. This also has the same property. It has limits and co-limits. We'll denote this by S sigma, the category of symmetric spectra. And the forgetful functor will preserve all the limits and co-limits. This category, the category of symmetric spectra with the stable model structure is also Quillen equivalent to the one we have discussed before, the homotopy category of orthogonal spectra and homotopy category of sequential spectra. So now once we are saying that all these two new categories that we have stated, the category of homotopy category of orthogonal spectra and symmetric spectra also satisfies all those 12 properties. So we should mention about the uniqueness. So here's the theorem which says that if a category is a stable model category, and if you have a equivalence of triangulated categories, so from stable homotopy category to the homotopy category of C, then this category is Quillen equivalent to the sequential spectra. So basically all those categories that we discussed are Quillen equivalent to the sequential category of sequential spectra. So if you remember that last of the chromatic homotopy theory talk, we saw the smash product, and that was the commutative smash product in sequential spectra, but we don't have commutative smash product in sequential spectra, but in the symmetric spectra. But because of this equivalence, we are using all are same as category of spectra. And the last about let's talk about the Spanier-Whitehead duality. So for this, we need the symmetric monadal structure on the category. So we have this symmetric category of symmetric spectra with this product operation as the smash product, and the unit element is the sphere spectrum. The statement says that if E is a spectrum and X is a finite CW complex, then the nth homology group of X is equal to the negative nth cohomology group of dual of X. So let's see, here's the definition of dual of object. Dual of X is an object Y equipped with these maps E from X smash Y to the unit and eta from unit to Y smash X. such that these compositions are canonical isomorphisms. Oh, sorry, I forgot to change. It is X. Sorry, it's typo. Sorry, it's a typo. We'll see the proof of that using this isomorphism, which is from, if you consider the homotopy classes of maps from Z smash Y to W is isomorphic to the homotopy classes of maps from Z to W smash X. So if we shift this up here, then it will be dual of the object. Y is dual of X. Then just use this isomorphism to get the required identity. And similarly for the cohomology part. Okay. So next proposition is about the dual. If X has a dual, then it is unique. And that is the internal function object from X to S naught. So we'll assume this, it exists in the stable homotopy category. So for that, we are just using the previous isomorphism and the unit lemma. Together, this will prove that if X has a dual and it is Y, then it is nothing but the internal function object. And the next remark is about if X has a dual and W and Z are in the objects in the symmetric spectra, then we have this isomorphism. Homomorphisms from W smash X to Z are isomorphic to the homomorphisms from W to dual of X smash Z. So we have seen this in homotopy category of topological spaces, but it is in the homotopy category, not just for before that, not in topological category, but it holds before going to the homotopy category, this isomorphism. And next, last three remarks as this D is a contravariant functor, and if X and Y are dual objects, and if you have a map between X to Y, then the co-fiber of that will again be dual. And so if you have a fibration and then apply if you have a co-fibration, then apply the contravariant functor D, you will get this, which will be a fibration in this category. And the last is which objects are dualizable, then the finite CW spectrums are dualizable. Okay, I think I have that's it. So thank you.
Any questions?
So we have serif fibrations, and in the homotopy category, the weak equivalences, am I saying right? So weak equivalences are homotopy equivalences, and the fibrations are serif fibrations. From that, we can obtain the Q fibrations, Q co-fibrations. In the homotopy category of topological spaces. In general, Q co-fibrations. This is in this category, right? Or they're also made? This is about the stable one.
Hello. Yeah, so maybe we can obtain Q co-fibrations by lifting properties with respect to fibrations that are given. So in model category, it's enough to know weak equivalences and one of the fibrations and co-fibrations. So we can obtain co-fibrations from that.
Any other questions?
You can think about any map that has a left lifting property with respect to all CW complexes. Yeah, that is a Q cofibration. I think. I preferred slides because there are so much to write. I couldn't cover that in time. So,
Okay, let us thank the speaker again.